As I said before, explaining theoretically these iterative methods is a much harder process than actually solving questions. And the exam questions that I have for you here are a proof of that. So let's look at the first one. This is Spring 2015, question paper 21. And I'll start, I have this question over here, question 5. It says, given that integral 0 to a of 3 e to the power of 1/2 of x plus 1 dx equals 10, show that the positive constant a satisfies the equation a equals 2 natural logarithm of 16 minus a over 6. All right, so you know that this stuff equals 10. So you can use this to get the value of a, right? So we need to integrate this and equal it to 10. I can break it apart into two integrals, all right? Extract the 3 out of the integral and just integrate that part between 0 and a. Same thing in relation to 1, okay? Then substitute the boundaries. And eventually, this is what I get. So I basically just have putting the e to the power of a over 2 on one side equals that. Then I have to get rid of this e, all right? And I do the natural logarithm on both sides. Natural logarithm of e to the power of a over 2 is just a over 2 equals natural logarithm of this. And I get the equation that I have in the first place just by sending this to the other side, all right? Then use the iterative formula a n plus 1 equals 2 natural logarithm of 16 minus a n over 6 with a1 equals 2 to find the value of a correct to 3 decimal places. Give the result of each iteration to 5 decimal places. Two things about the question. First, in most situations, you are going to be given the iterative formula. You don't have to guess how you're going to rearrange the original equation to get the iterative formula. Then, in most situations, you are also going to be given the number of decimal places that you have to write down as you look for the value of the root, or a in this case. So the final result needs to be correct to 3 decimal places, your final answer, but your search will have to be will have to contain 5 decimal places. So basically, what does this mean? It tells you where to start. Actually, it's 2. All right. So substitute here by this value by 2, and this is what you'll get. Now you're going to substitute that value by this, and this is what you get. You don't have to write down, for example, over here, 2 natural logarithm of 16 minus 1.69460 divided by 6. No, you don't have to do that. This will take forever. This should be already in your calculator. You just, every time you get the value, just use the cursor to find the value that is changing all the time and just substitute that, all right? Everything else stays the same. So put it there, click enter or OK or whatever. Your result, write it down. Then just write f of that, put it there, press enter, write it down, put it again in a calculator, press enter, write it down, and do that. Look here, 5 decimal places as they asked. Each one of the values that you use to get the final result. And eventually, when you see that the number of decimal places that they ask for the final answer, which in this case was 3, stays the same, all right? You may write it down with confidence that correct to 3 decimal places, the result of this would be 1.732. Let me just see here one thing. Yeah, this is not supposed to be x, it's supposed to be a, but you know what I mean, all right? Yeah, that's it. Next question. This is paper 2, November 2007. Question 2. The sequence of values given by the iterative formula x of n plus 1 equals 2x of n over 3 plus 4 over x of n squared with initial value x1 equals 2 converges to alpha. Use this iterative formula to determine alpha correct to 2 decimal places, giving the result of each iteration to 4 decimal places. Again, it's telling you how many decimal places you should use as you look for alpha. And it tells you also that alpha should be correct to 2 decimal places. So let's just do what I tell us to do. Here you have the iterative formula. It tells you where to start. Start substituting this by 2. Again, just write this down on a calculator. The only thing that you'll have to substitute is this value and this value over here under that square. Do that, you have this value. Write it down. Just write then f of it, 4 decimal places as they asked. Press enter, you have this. Write it down. Write also f of that stuff. Put it in your calculator. Press enter. And continue doing this until you are confident of the number of decimal places that you have to present, which in this case was 2. Notice that these two round to 2.29, but I wanted to ensure that actually here I could go up to 3 decimal places. I did one more than I needed. Anyway, it doesn't matter. I'm completely confident that the result is 2.29. Then state an equation that is satisfied by alpha and hence find the exact value of alpha. All right, based on that iterative formula, I know that the original equation was x equals 2x over 3 plus 4 over x squared. Here you are just doing the opposite of what normal procedure is, which is getting the expression of x equals big F of x, and then transforming this into the iterative formula. Here you start with the iterative formula, and you have to get the original equation, x equals big F of x. And now from this, you have to get the equation small f of x equals 0. What did I do? I just found the same denominator, which in this case will be 3x squared. So I have to multiply this by 3x squared. I have to multiply this by x squared, and I have to multiply this by x. And I can eliminate straight away the denominator. So I did all of this in one go. And then eventually, I just solve the equation, and I get the value of x as being cube root of 12. And this is precise to an infinite number of significant figures. Can try it in a calculator and compare it with that. This is the value correct to an infinite number of significant figures. This is only correct to two decimal places or 3 significant figures. Last exam question. It's a November 2009, paper 22, question 7. You are given this, and it says that the diagram shows the curve y equals x squared cosine of x for x between 0 and pi over 2, and its maximum point, m. Show by differentiation that the x-coordinate of m satisfies the equation tan of x equals 2 over x. If m is a maximum point, then dy by dx equals 0 will give you the x-coordinate of m and eventually lead into that. So let's do this. Wait. This is it. So dy by dx is what? You have a product of 2 smaller functions. So differentiate the first times the second plus the first times the second differentiated. That's what I did. All right. I equal it to 0. I can divide the whole thing by x. So I just have 2 cosine of x equals minus x sine of x. Send this to the other side. Then arrange it to get to what I want. Tan of x is sine over cosine, so I send the cosine over here and the x over there, and that's what I get. Then, question 2. Verify by calculation that this equation has a root in radians between 1 and 1.2. So you already know what to do in these cases. if you have to prove that the root is in between an interval, do f of the boundaries of that interval. They should have opposite signs. Let's see. So f of 1 is a negative number, f of 1.2 is a positive number. The product of f of 1 by f of 1.2 is negative, and this proves that the 0 is in between these two. Finally, I think it's finally, yes, finally, use the iterative formula x of n plus 1 equals tan negative 1 of 2 over x of n to determine this root, correct to 2 decimal places. Give the result of each iteration to 4 decimal places. It's the same stuff all over again. In this case, they use this to do x equals tan negative 1 of 2 over x. They adapted that for this iterative formula. They tell you where to start, 1, and again, it's the same thing. But 1 over there, and you get 10 minus 1 of 2, which is that result, correct to 4 decimal places. Now, in a calculator, do f of 1.1071. This is what you get. Write it down. Do in a calculator f of 1.0652. This is what you get. Continue doing this until you have results that will give you the 0 correct to the number of decimal places that you are asked to begin with. In this case, it was 2. So at this point, you are completely confident to say that x is 1.08 correct to 2 decimal places.